Today I shall discuss a very important theorem or rather theory in the theory of partial differential operators. It is called the Atiyah-Singer index theorem. But I shall emphasize its application to quantum field theory, especially in the calculation of gauge anomalies, and we shall show that when there are gauge anomalies, that is the path measure is no longer invariant under a gauge transformation, then certain currents do not fail to be conserved, and the amount by which they fail to be conserved is related to the index of the Dirac operator. It is related to the index of the Dirac operator, and it is also related to the fermion asymmetry, that is the non-zero value, that is to a non-zero value of the number of 0 modes of the Dirac operator corresponding to +1 eigenvalue of gamma 5, and those corresponding to, and the 0 modes of the Dirac operator corresponding to -1 eigenvalues of gamma 5. So, Sherall asymmetry, then lack of gauge invariance, anomalies, and the Atiyah-Singer index theorem, these are all related, and we shall see how exactly this relation comes up. So, to start with, what I shall do is I shall consider an action which is a function of the fermionic fields psi and psi bar, for example the Dirac action, okay. And let us say you are considering a path integral for this action. So, let us take h cross as 1 deep psi bar. This is a path integral, and I want, okay, now this path integral will obviously be invariant under any change of the integration variable, namely psi x, the field psi x. But what happens is the path measure is no longer invariant. That means if you are dealing with left chiral or right chiral fermions, then a left chiral fermion corresponds to an eigenvalue of 1 for gamma 5, and a right chiral fermion corresponds to an eigenvalue -1 for psi. So, in other words, if I have a solution to Dirac's equation, say the 0 mode of the Dirac's equation, I call D is given by gamma mu d mu, where d mu is the Dirac operator, which is equal to dou mu plus IE A mu, where A mu is a Lie algebra field, a gauge field, a non-abelian gauge field. That means A mu takes values in the Lie algebra, where G is the Lie algebra of a Lie group, which is a subgroup of UN. So, this is the D is the Dirac operator, and let us say there is no mass, you are dealing with a massless fermion. So, D has, you are looking at solutions of such equations, d psi equal to 0, that is 0 modes of the Dirac operator. Now, gamma mu anti-commutes with gamma 5, gamma mu anti-commutes with gamma 5 for all mu equals 0, 1, 2 and 3, where gamma 5 is gamma 0, gamma 1, gamma 2, gamma 3, and this can be expressed as I 0, 0 minus I, whereas I is a 2 cross 2 identity matrix. So, because they do not commute, because they anti-commute, it follows that if d psi equals 0 for some psi, you can also write this as gamma mu d mu psi equal to 0, then multiplying it by gamma 5, I get gamma 5 gamma mu d mu psi 0, or since they anti-commute, you can write this as gamma mu d mu gamma 5 psi, the negative sign, that is 0. In other words, gamma 5 psi is also a 0 mode of the Dirac operator. You can look at non-zero eigenvalues. If you have a non-zero eigenvalue for the Dirac operator, say gamma mu d mu acting on psi is lambda times psi, where lambda is non-zero, then by operating on gamma 5 on both sides and using the anti-commutativity of gamma mu with gamma 5, remember that d mu is the Yang-Mills gauge covariant derivative, dou mu plus IE A mu, or where A mu is equal to A mu alpha, tau alpha. Tau alphas are Hermitian operators, they are the generators of the Lie algebra of the gauge group. So, this will imply on multiplying by gamma 5 that gamma mu d mu acting on gamma 5 psi is equal to minus lambda gamma 5 psi. That means if gamma 5 psi, if psi is an eigenvalue, if psi is an eigenvector of the Dirac operator, is an eigenfunction of the Dirac operator with a non-zero eigenvalue lambda, then gamma 5 is also an eigenvector of, is also an eigenfunction of the Dirac operator, but with a eigenvalue of minus lambda. So you can see that the positive and negative, that is the non-zero eigenvalues of the Dirac operator, they get paired up. So that means that if you look at the number of eigenvalues, number of eigenfunctions, the dimensions of the eigenspace of the Dirac operator corresponding to a non-zero eigenvalue lambda, it is same as the dimension of the eigenspace of the same Dirac operator corresponding to a non-zero value minus lambda, but the zero eigenvalues need not be paired up. So what happens is that if you take a zero eigenvalue, a zero eigenfunction d psi equal to 0, that is gamma mu d mu psi equal to 0, then it will follow that gamma mu d mu gamma phi psi is also 0. So it will follow in particular that gamma mu d mu times 1 plus gamma phi by 2 psi, this is 0, and gamma mu d mu 1 minus gamma phi by 2 psi is also 0. So if psi is not 0, then either 1 plus gamma phi by 2 psi is non-zero or 1 minus gamma phi by 2 is non-zero. If both 1 plus gamma phi by 2 and psi and 1 minus gamma phi by 2 psi are non-zero, then you get a pairing up of a zero mode of the Dirac operator with that is 1 plus gamma phi by 2 psi, 1 plus gamma phi by 2 is the projection onto the plus 1 eigen subspace, plus 1 eigenvalue eigen subspace of gamma phi, and 1 minus gamma phi by 2 is a projection onto, is orthogonal projection onto the minus 1 eigenvalue subspace of gamma phi. Essentially if you look at this acting on psi, you put gamma phi, then this is 1 plus gamma phi by 2 psi. So 1 plus gamma phi by 2 is a left hander fermion, and gamma phi into 1 minus gamma phi by 2 psi is equal to minus of 1 minus gamma phi by 2 psi. So 1 minus gamma phi by 2 is a right-handed fermion, but it can happen that 1 minus gamma phi by 2 psi may become 0 or 1 plus gamma phi by 2 psi may become 0, that is possible, and that means that the zero eigenvalues of the Dirac operator, the zero eigenmodes of the Dirac operator, they need not be paired up, right. On the other hand, if lambda is a non-zero eigenvalue, lambda is a non-zero eigenvalue of the Dirac operator, then you have the relation that 1 plus gamma phi by 2 psi is equal to, because of the anti-commutativity of gamma phi and gamma mu, this is lambda into, if you pre-multiply by 1 minus gamma phi by 2, you note that 1 minus gamma phi by 2 d is same as d into 1 plus gamma phi by 2, because of the anti-commutativity of gamma mu and d. So this is 1 minus gamma phi by 2 psi, and likewise d acting on 1 minus gamma phi by 2 psi is lambda times 1 plus gamma phi by 2 psi. That is, you can have a situation in which if 1 plus gamma phi by 2 psi is 0, then this equation will imply that 1 minus gamma phi by 2 psi will also be 0, because you are assuming that lambda is non-zero. That means psi itself will become 0, it is no longer an eigenfunction. This means that if psi is an eigenfunction of the Dirac operator, Dirac-Yang-Mills operator corresponding to a non-zero eigenvalue, then both 1 plus gamma phi by 2 psi and 1 minus gamma phi by 2 psi will be non-zero. So in particular if 1 plus gamma phi by 2 psi is 0, then 1 minus gamma phi by 2 psi will also become 0, so that cannot happen. So both of them are non-zero, which means in particular that gamma phi psi is non-zero. Gamma phi psi is, of course, that will be non-zero. So psi is an eigenvalue, gamma phi psi is an eigenfunction of the Dirac operator with eigenvalue if psi is an eigenfunction of the Dirac operator with an eigenvalue lambda, then gamma phi psi is an eigenfunction of the Dirac operator with an eigenvalue minus lambda, and pairing will take place. So what happens is that if you look at now how an anomaly can arise, suppose you consider the path integral e power I psi bar d psi bar, and psi is a fermion, left-hander fermion. I want to look at gauge transformations in which T belongs to a Lie algebra generator of the gauge group. That means D is a that means that T is a Hermitian operator in particular, and I consider T gamma phi, that means this is a shorthand notation for T tensor gamma phi. So e power I T gamma phi, e power I alpha x T into gamma phi, this acts on the wave function psi x to change it. This is a chiral, it is a chiral gauge transformation, it is a chiral gauge transformation because you are including the factor gamma phi here. So, and alpha is assumed to be an infinitesimal real valued function of time. So, this can also be, this transformation of the wave function can also be written as delta psi x is equal to I alpha x T gamma phi acting on psi x, or equivalently you can say okay. So, what happens to delta psi bar x then? Remember that psi bar x is defined to be psi x into gamma 0. So, this is equal to you use the fact that T is a Hermitian operator. So, this is minus I alpha x, alpha is a real valued function of type, real valued function of the space time arguments. So, psi x star, just let me erase this, psi x star. Then here you have T gamma phi, because T is Hermitian, gamma phi is Hermitian, and then gamma 0. So, gamma 0 anti-commutes with gamma phi. So, this will become I alpha x psi star x gamma 0 T gamma phi, which is equal to I alpha x psi bar x T gamma phi. That means that T into gamma phi into, so you have to put a delta because you are looking at the variation. So, delta psi star, delta psi, delta psi star, delta psi bar. This means that what I am trying to say is that if psi goes to psi x, it goes to psi x into 1 plus I alpha x T gamma phi into psi x, an infinitesimal chiral gauge transformation. Infinitesimal chiral gauge transformation. Of course, it is a unitary operator because T is Hermitian, gamma phi is also Hermitian. So, it is a unitary operator, but unfortunately psi bar x will also have the same transformation law, namely 1 plus I alpha x T gamma phi into psi x. That means that if you look at the path measure d psi bar, which is same as saying the product over all d psi x, d psi bar x, x varying over R4. This is the path measure. This path measure will change by, this will also, both d psi and d psi bar will change by the same amount. So, this path measure d psi bar, this will go to 1 plus trace of I alpha x T gamma phi the operator looked upon as a kernel delta 4 x minus y, looked upon as a kernel into d psi bar. See, what happens is that if you take any vector, for example any vector xi, suppose this undergoes a transformation of the form, an infinitesimal transformation of the form 1 plus epsilon times a matrix valued function of x times xi, or 1 plus epsilon times a matrix times xi, this is an infinitesimal parameter, then how much does d xi change by? D xi according to the Jacobian rule changes by determinant of 1 plus epsilon f into d xi. It changes by so much, and determinant 1 plus epsilon f can be written as determinant of e power epsilon f plus order epsilon square into d psi, which is equal to e power epsilon trace f plus order epsilon square into d xi, right, which is equal to 1 plus epsilon trace of f, 1 plus epsilon trace of f into d psi. That means the path measure d psi changes by an amount 1 plus epsilon trace of f d psi, or equivalently I can say that the path measure, the integration measure changes by an amount epsilon trace of f into d psi into d xi. okay, into d xi. I should write this as xi. D xi changes by this much, right, according to the Jacobian rule. So if you use that fact, what happens is that deep psi bar, it's a product over all the x's, right. This is equal to the product over all x varying over R4 deep psi x bar. So this is going to change by 1 plus trace of I alpha x and then t gamma phi into delta 4 x minus y, the trace of this kernel, because this acts as the identity operator acting on functions, which means that this trace will evaluate to how much? This trace will evaluate to trace of I alpha x gamma phi t. That to evaluate the trace of a kernel I must put x is equal to y, that means it will become delta 4 x minus x d4x, which is absurd, it makes no sense. So is there a correct way by which I can evaluate this using some sort of using a gauge invariant version of this trace? So the answer is very clear. It has been discovered by physicists. It is also discussed in the celebrated book of Weinberg volume 2 on the quantum theory of fields. It says that you don't have to do anything. Wherever you have delta 4 x minus x coming into the picture, you can replace delta 4 x minus y by 1 upon 2 pi power 4 integral e power I k dot x minus y d4k, and then you act on this function. This is an identity kernel. You act on this function by d square by m square. Okay, you act on this function by d square by m square, where d is the Dirac operator gamma dot d, or equally gamma mu d mu, which is gamma mu dou mu plus IE a mu, where a mu is the Yang-Mills operator. A mu is the Yang-Mills potential. So I act on this by this, and here also I will act on this by the same thing. So this will be f of d square by m square, and I will let m go to infinity. In the limit that m goes to infinity, f of d square by m square becomes f0, right, which is a constant into delta 4 x minus y you get. So you will evaluate the trace of this operator in this form. So and then I will put x is equal to x. So the change in the path measure, delta deep psi bar, this can be written as simply f of d square by m square acting on integral e power I k dot x minus y d4k, and this is nothing but how does d act on e power I k dot x minus y, I k dot x minus y, how does it act on this as an operator? If you look upon this as a multiplication operator and d as a differential operator in the x variable, then this can be written as e power I k dot x minus y into d plus d acting on this, which will give you what is d? D is gamma dot d or gamma mu d mu. So if you differentiate this with respect to mu, what do you get? Dou mu. So if I differentiate this with respect to x, what do I get? I get plus I gamma mu k mu. I gamma mu k mu I gamma mu k mu plus I e a mu, I e gamma mu a mu. If I differentiate, if I apply dou mu plus I e a mu, if I apply this to e power I k dot x minus y, if I look upon it as a function, then this will dou mu acting on this will give you I. So I k mu plus I e a mu acting on the same thing e power I k dot x minus y. So that is how you get this term here, I e gamma mu a mu. So this can be written as, in other words, I can write d in terms of operator as an operator. If I look upon e power I k dot x minus y as a multiplication operator, then this can be written as I gamma dot k plus E times gamma dot a into e power I k dot x minus y plus d, or it should be, no, this gamma dot a, it won't, the d won't come, this here you will have a dou mu only, that is gamma dou you will have, dou is given by gamma mu dou mu. So as a differential operator what will happen is that d acting on e power I k dot x minus y will give you e power I k dot x minus y d plus e power I k dot x minus y times I gamma dot k, or equivalently this will be e power I k dot x minus y into I gamma dot k plus d, right. So in particular if you apply this repeatedly, you can apply it repeatedly, d power n acting on e power I k dot x minus y as an operator, this will give you if you operate it once, what do you get? If you operate it once you get I gamma dot k, you get e power I k dot x minus y into I gamma dot k plus d. So if I again apply d square to this, I again apply d square to this, again I will get square, like that d power n, if I apply 10 times I will get this whole thing to the power n. So for any function, smooth function, f of d square by m square acting on e power I k dot x minus y, this will give you e power I k dot x minus y times f of I gamma dot k plus d square by m square, right. And I am now interested in acting on this operator on the function 1 which takes the value 1. So what I get is that f of d square by m square acting on e power I k dot x minus y acting on 1, that means this acts on this function as a function alone. This is simply equal to when you put and you are not put x is equal to y here, right. So I get simply e power I k dot x minus y into f of I gamma dot k plus d square divided by m square, and then I act on this by on the unit vector on the unit function to get a function. So this when I act on it when I act on the constant function 1, it amounts to acting on this function. So as a function this assumes this form, and then I am going to integrate with respect to k. I am going to put a trace of, to calculate the anomaly, I am going to put a gamma 5 t here, and I am going to calculate this trace, and then I am going to put x is equal to y here or y equal to x, and then I am going to multiply it by alpha x and integrate over all x, that is the gauge anomaly which I get into I. So if I do the same thing on this side, what do I get? I put x is equal to y, this goes off, then I act on this by 1, then I multiply it by trace of, I multiply it by gamma phi t and take the trace of this quantity, and then I multiply it by alpha x, and then I integrate over all space time integral. So that gives you the gauge anomaly. That gives you the anomaly in the path integral caused by a chiral transformation, a chiral gauge transformation, the change in the path integral applied to the path measure caused by a chiral gauge transformation. So now if I want to evaluate this, how do I go about doing it? You look at f of I gamma dot k plus d square divided by m square. This can be written as f of minus k square plus d square, k square by m square plus d square by m square plus the anti-commutator between I gamma dot k and d plus, okay, and then I expand this around. I am going to, in the end I am going to let m go to infinity. So I want to calculate this quantity acting on 1, this operator acting on 1 multiplied by gamma 5t, take the trace of this, and of course multiplied by alpha x and take d4x, and then d4k also, right. So f is some sort of a regulatory function, it is a regulator, it prevents the delta function from blowing up, that is by replacing e power I k dot x minus x d4k. This is a delta function, this does not make any sense, right, d4k, this is delta 4 x minus x, this does not make any sense, but if I replace it, I have replaced it by f of d square by m square acting on e power I k dot x minus y, evaluated this at y equal to x, and then I give meaning to this integral after multiplying it by alpha x and so on, and let m go to infinity. In the limit as m goes to infinity, this reduces to this provided f0 is 0. So if you evaluate this, what do you get using the Taylor expansion? Do not evaluate it using the Taylor expansion as yet, right now. Make a change of the variable, put k by m, replace k by m by k, that is replace k by the 4 vector k mu by m into k, then the d4k will become m power 4 d4k. So this will become trace of gamma 5 t, and here you will have f of minus k square plus d square by m square plus d square by m square plus okay, there is an m square also here, plus 1 by m square. So plus 1 by m square times this anti-commutator I gamma dot k comma d plus evaluated at 1 acting on 1 into alpha x into d4k, and since you have to put a factor of m power 4 here because you are replacing the integration variable k by m into k, so d4k will go to m power 4 into d4k. Now make a Taylor expansion of all this around the point minus k square. So this will become integral trace of gamma 5 t f of minus k square plus I gamma dot k comma gamma dot d or d gamma dot k plus d plus the anti-commutator, and it is divided by m square, so I had put m there, so this will become this divided by m plus d square by m square acting on 1 into alpha x into d4k d4x. This is what is the gauge anomaly after multiplying it by a factor of I. So this can be written as f of minus k square plus f dash of minus k square times these two terms. So this will become I gamma dot k comma d plus by m plus d square by m square acting on 1 plus half f double dash of k minus k square into the square of this quantity. The square of this quantity is I gamma dot k comma d plus d square by m square, whole this thing and whole square of this. You see now many terms will cancel out when you take that trace, because f of minus k square into gamma 5 t, the first term that you get is t gamma 5 into f of minus k square. So trace of this I get into f of minus k square. Okay, this trace is 0 because trace of t is 0 because it belongs to the Lie algebra of G, which is a subalgebra of skew Hermitian matrices, or even if t is not 0, trace of gamma 5 is going to be 0, right. Trace of t gamma 5, what does it mean? It means trace of t tensor gamma 5, which is trace of t times trace of gamma 5, and trace of gamma 5 is 0. So that term will cancel out. Now the term involving a single Dirac matrix trace of gamma, that will become 0. So this term will also not contribute to the trace. That is, if you multiply it by trace of gamma 5 gamma mu, that is also 0. Trace of gamma 5 gamma mu is also 0. The only terms which will contribute to the trace of gamma matrices are when there are product of 4 gammas coming to the picture and then multiplied by gamma 5. So this term will drop out, this term will become, this is d square by m square, this contains only the Yang-Mills matrices, Yang-Mills generator matrices, namely the TJs. So the trace of gamma 5, trace of gamma 5 multiplied by t multiplied by d square, that will also be 0, because gamma, it will factor out in the product of the trace of gamma 5 and the trace of t d square, and trace of gamma 5 is 0. The second, this term, if you look at this term, what will you get? You will get I gamma dot k comma, you will get I gamma dot k comma d, you will get I gamma k comma d, and you are having a square, you are having this plus d square. So 1 upon m plus d square by m square whole square you are having. So one term which will come here is I gamma dot k comma d square by m square. This contains 2 Dirac gamma matrices. After multiplied by gamma 5, there will be 3 Dirac gamma matrices whose trace is 0. So this will not contribute to the whole sub, but gamma dot k, no, you have to be careful here, you cannot just say that this is 0 very simply. You have to evaluate trace of gamma 5 and then gamma dot k comma d square. If you evaluate this thing, of course you are taking a commutator, you are taking an anti-commutator. So if you take a typical term, for example gamma dot k into d, which is gamma dot k into gamma dot d, and then you square it. Suppose you look at such a term, for example, into gamma 5, trace of this, what do you get? Gamma dot k, this can be written as gamma mu, gamma nu, k mu, d nu into gamma 5. Of course square of this, you can write it as the square of this. So this will be gamma mu, gamma 5, gamma mu, gamma nu, gamma rho, gamma sigma into k mu d nu, k mu, k rho, d nu d sigma, and then you put a trace here. Now trace of this quantity 4 gamma matrices multiplied by gamma 5 is the completely antisymmetric tensor in 4 variables, in 4 space time arguments, epsilon mu nu rho sigma into k mu k rho into d nu d sigma, and obviously this is 0 because this is the product k mu k rho is symmetric in mu and rho, whereas this is asymmetric in mu and rho. So this will also not contribute to the, trace. So the only thing which will contribute to the trace will be when you square, the only term which will contribute will come from the square of d square by m square. So you will get in effect m power 4 times, you need not go higher orders than m power 4 because you are multiplying by m power 4 after the change of variables. So it becomes it becomes m power 4 into f double dash at minus k square, m power 4 times d power 4 by m power 4. Okay, this will cancel out, and you are looking at the trace of this quantity. So trace of this quantity after multiplying it by a gamma 5t, and then you are acting this on 1, and then you are multiplying it by alpha x and integrating with respect to both k as well as x. That is going to give you the anomaly after you put a factor of I. So what is d4 acting on 1? d4 is gamma mu dou mu plus I e a mu. This is gamma dot d, and you are taking the power 4 acting on 1. You can clearly see that the only term which will contribute to the trace after multiplying by gamma 5, you multiply this by gamma 5 and take the trace, then what happens? Only gamma 5 into when 4 of the Dirac matrices come, namely gamma mu, gamma nu, gamma rho, gamma sigma. Similarly here you have, if I call this as d mu, then this is d mu, d nu, d rho, d sigma. And then you are of course going to take a trace of the Yang-Mills over the Yang-Mills operators also, Yang-Mills matrices also. So trace of this into trace of this, higher than, you do not go higher than second order derivatives in f because they will contribute 1 by m power 5, 1 by m power 6, 1 by m power 7, and after multiplying by m power 4 they will go down to 0, as m goes to infinity, because m power 4 into 1 by m power 5 is 1 upon m, m power 4 into 1 by m power 6 is 1 upon m square, and all these terms will go to 0 as m goes to infinity. So you are left with just this much. So what does this evaluate to? If you make a change of the variable, k0 goes to I k0 so that it becomes a Euclidean integral, then the integral with respect to k square becomes f of k square into d4k over Euclidean space, which is f double dash of k square times a constant times k cube dk, which can be written as f double dash of s, where k goes from 0 to infinity, f double dash of k square into k cube, that is f double dash of s into ds, it will be of this form, and f double dash of s into ds, that will be by integration by parts s integral g, which will go to 0 to infinity, minus integral f dash integral g, f dash s ds from 0 to infinity, which will be f dash of 0, which will be f of 0, which is 1. So in effect what will you get? You will get epsilon mu nu rho sigma, that m power 4 will cancel out with m power 4 outside, and it will give you f, it will give you d mu, d nu, d rho, d sigma. Will get this sort of a term after taking the trace over m, and then you have to take a trace of this acting on 1, and then you multiply it by alpha x, and you have a factor, you have a f0 factor which is 1, and then you are integrating this over x. So by putting the regulatory function f, you have skipped the problems avoided by the singularity of the delta function. Now of course you can ask a question, why instead of replacing the delta function by this sort of a thing, k dot x minus y d4k, and then letting m go to infinity, why cannot you put f of simply dou square by m square, where dou is the ordinary Dirac operator without any gauge connection? Then you will not get a gauge invariant theory, because dou mu is not a gauge covariant derivative, whereas dou mu plus IE a mu is a gauge covariant derivative. That is why you will not get that problem. Now this is completely antisymmetric, so this quantity is the same as epsilon mu nu rho sigma. I can antisymmetrize between mu and nu, d mu and d nu, and put a factor of half here. Because epsilon mu nu rho sigma is antisymmetric in mu and nu. Likewise I can antisymmetrize rho and sigma and write it as d rho comma d sigma acting on 1. But what is this? This is nothing but the Yang-Mills field tensor, right? If you look at d mu comma d mu, this is nothing but dou mu plus IE a mu comma dou nu plus IE a nu, which is a Yang-Mills tensor, which is nothing but f mu nu into IE at x, where f mu nu is nothing but dou mu a nu minus dou nu a mu plus IE a mu comma a nu. This is the Yang-Mills field tensor. So what you get for the anomaly, what do you get? You get trace of t into gamma, trace of t times trace of t into f mu nu, f rho sigma at x multiplied by epsilon mu nu rho sigma d4x into of course alpha x, I alpha x. But you see the Yang-Mills tensor can also be written in terms of the Lie algebra basis. So I can write this as f mu nu a of x into Ta, where Ta's are the generators of the Yang-Mills gauge group. So this becomes nothing but trace of t, Ta, Tb multiplied by alpha x into I multiplied by f mu nu a x f b rho sigma x d4x, right, integral of this into I alpha x d4x. So this is precisely the gauge anomaly, the anomaly coming from the lack of invariance of the path measure. In the particular case, when I take t as the identity, then I can choose the Lie algebra basis vectors. I can choose the Lie algebra basis such that Ta, Tb is some constant times delta Ab. So in that case this assumes a particularly simple form, namely the gauge anomaly, that is under a change of measure, under a change of the wave function, under a change of the wave function in the path measure given by a gauge chiral transformation. This goes to 1 plus I alpha x gamma phi t acting on psi x. Under such a change in the path measure goes to p, the path integral goes to p plus delta p, where delta p is given by I times integral alpha x into a normalization factor n into fa mu nu x fb rho sigma x into epsilon mu nu rho sigma into d4x. So, this is what is the anomaly. How do you interpret this anomaly? It is very simple. You see, suppose you look at the path integral, it is I psi psi bar d psi bar. Now, because there is a change in this path measure described by the quantity which I got, which I just wrote down, the change in this I can have to add in order, since the entire path integral has to be invariant under any change of variables. The only way out is that this action integral must change by a small negative of the amount by which this path changes. In other words, for this path to remain integral, this path integral to remain invariant under the chiral gauge transformation, for this path integral to remain invariant under the chiral gauge transformation, it must follow that since d psi bar, this goes to I alpha x times fa mu nu x fb rho sigma x epsilon mu nu rho sigma into d4x. Since this goes to this, the only way is that I must change by the Lagrangian. If you write I as I psi bar as integral L psi bar dou mu psi bar d4x, then it is equivalent to saying that L changes to L plus delta L. L changes to L plus delta L, so that the total path integral remains invariant because it is a change of variable, and that is possible only by, since this is an infinitesimal quantity, I can write e power I delta L as 1 plus I delta L. In other words, what I require is that I times delta L d4x plus I times integral of this quantity alpha x into all this f mu nu a, all these anomalies which I calculated, the sum of these two must be 0 because the entire path integral should not change. That is equivalent to saying that delta L must be equal to this quantity. It must be equal to this quantity. Now you already know that, suppose I has global gauge invariance. Say I psi bar is invariant under a global gauge transformation. What is the meaning of global gauge transformation? It means you are replacing alpha x by a constant alpha naught, right? That means you are applying the change psi goes to e power I alpha naught into t gamma phi multiplied by psi x, where alpha naught is a constant, or equivalent to an infinitesimal transformation 1 plus alpha naught t gamma phi psi x. It is a global gauge transformation. Suppose I is invariant under this. This happens, for example, in the Dirac equation with any sort of potential, with any sort of gauge potential, then it is obviously invariant. For example, if you look at the Dirac Lagrangian, what happens? Dirac Lagrangian is psi bar into gamma mu into I dou mu plus E a mu into psi, let us say minus m into psi. So if you change psi by e power I theta psi where theta is a constant, this is going to remain invariant irrespective of whether you change mu or not. So under a global gauge transformation this is invariant. Then what happens if you try to promote this invariance to a local gauge invariance? That means if alpha naught is no longer a function, is no longer a constant, but it is alpha x, a function of space time, then obviously your change in the Lagrangian, or change in the action, the change in the action must be of the form integral of j mu x dou mu alpha x d4x. That is because the Lagrangian is first order in space time derivatives, and when alpha is alpha naught this should become 0, so it should have this form. So what I require is that where j mu is some sort of a no-other current, associated with the symmetry group, So the symmetry group of global gauge transformation. So j mu x into dou mu alpha x d4x, this is a change in the Lagrangian, and I times this plus you must have I times the anomaly alpha x, the change in the path integral due to the path measure, this is a change in the path integral due to the change in the action under a local gauge transformation. This must have the form epsilon mu nu rho sigma into Fa mu nu Fb rho sigma x d4x. This must be 0, and this must be true for all alpha x, dou mu of alpha x. So this is possible only if you integrate by parts, this becomes a violation of the gauge current conservation. So dou mu of j mu x must be equal to epsilon mu nu rho sigma into Fa mu nu x Fb rho sigma x. That is, the current is no longer conserved due to the anomaly. Due to this anomaly of the, when you apply a chiral gauge transformation, the current is no longer conserved, but it is equal to this anomaly. This is the analogous of E dot B term appearing in Maxwell's theory. In Maxwell's theory, you have in the Lagrangian only a E square minus B square term, you do not have an E dot B term. This is something like a monopole. Okay, and you note that in the language's differential forms, this can also be written as Fa wedge Fb. Sorry, it should have been Fa, you are summing over A. This is same as Fa wedge Fa, or equivalently trace of F wedge F, right. So the gauge anomaly, the anomaly in the current conservation is how much? It is given by integral alpha x into trace of Fx wedge Fx. Okay, and you see that this has got, when alpha x is equal to 1, or when alpha x is alpha naught, then this has got the form integral trace of F wedge F, where F is a 2 form. F is the 2 form given by F mu nu x dx mu wedge dx nu. So that this becomes a 4 form, which means it is an ordinary 4-dimensional integral. This is what appears in the Atiyah-Singer index theorem in flat space time. So there must be some connection, you suspect that there must be some connection between this gauge anomaly and the Atiyah-Singer index theorem, and let us see indeed how it comes. Okay. So of course in the Atiyah-Singer index theorem, you have, in the most general form, you have a Yang-Mills operator of this form. So this is gamma mu dou mu plus IE mu, where you have a Yang-Mills operator and you also have a connection of the gravitational field, everything is there. Gamma mu becomes a local gamma function, that is, gamma mu becomes a function of x. In terms of the tetrad, this will become gamma a e mu ax, and you note that gamma mu x comma gamma nu x, this anti-commutator, this will be nothing but gamma a comma gamma b plus anti-commutator into e mu a e nu bx, where e mu is the tetrad, and gamma a comma gamma b plus is 2 eta ab. So this is 2 eta ab times e mu ax e nu bx, which is equal to 2 g mu nu x. That means when you use local Dirac matrices, local Dirac gamma matrices defined by a local inertial frame, then they satisfy the anti-commutation relation gamma mu x comma gamma nu x plus. This plus is nothing but 2 g mu nu x. Whereas when you use constant Dirac matrices gamma a comma gamma b, this becomes twice the Minkowski metric. So this is the relationship between the two situations. So now when you use a Dirac Yang-Mills gamma operator, a Dirac Yang-Mills operator of this form, where you have both Riemannian connection, a spin connection of the gravitational field as well as a Yang-Mills connection. That means you have a connection on the space-time manifold as well as a connection on the fiber space where the Yang-Mills fields act. Okay, where the Yang-Mills fields takes value, let us say like a principal bundle that you are thinking of. Then in that case, your gamma mu x into del mu can be written as gamma mu x gamma a e mu ax multiplied by dou mu plus IE a mu x. So this is the Dirac Yang-Mills operator in curved space-time. In that case, you won't get f wedge f, you will get, if you calculate the index of this operator by squaring, this is called the Dirac operator. If I square it, if I square D, then there is something called Lichner-Ovich formula for the square of the Dirac operator. So it will give you several terms, right? It will give you several terms. It will give you a term like first a covariant Laplacian it will give you of the form say it will be a covariant Laplacian of the form G mu nu del mu del nu. It will give you a term like this. It will give you a curvature term. It will give you a curvature term. It will also give you a curvature of the Yang-Mills term. It will give you several terms, a curvature of the space-time manifold and a curvature of the Yang-Mills connection. It will give you all these terms. This is called Lichner-Ovich formula under Laplacian, where del mu is a gauge covariant, is the covariant derivative with both the gauge field as well as the spinor connection taken into account. Right? This is of the form dou mu plus IE dou mu plus IE a mu, dou mu plus IE a mu plus gamma mu, where gamma mu is the spin connection of the gravitational field and a mu is the Yang-Mills connection. So in that case, if you try to calculate e power minus t d square and its super trace, you calculate its super trace and let then this is precisely the index of the Dirac operator. It can be seen by the following way. You can write d as the Dirac operator as 0 d plus d minus 0, where d minus is d plus star. You can write it in this form by using the expression for the local gamma matrices. Gamma A can be written as 0 sigma A minus sigma A 0, A equal to 1 2 3, and gamma 0 can be written as 0 I 0. So by using this you can write this in this form, so that what happens to d star d? D star d becomes 0 d plus star d minus star 0 into 0 d plus d minus 0, which is d minus star d minus 0 0 d plus star d plus, which is equal to since d minus star is same as d minus is minus of d plus star. So this will be equal to d plus d plus star 0 0 d minus star d minus d plus star d plus star d plus. So if you compute and d star is of course minus d square is minus d, so this is minus of d square. So in other words, the index of d square, if you look at the super trace of e power minus t d square, that is nothing but the super trace of this matrix e power minus t. This will come out to be a trace of e power minus t d plus star minus trace of e power minus t d plus star d plus. And since the non-zero eigenvalues of a Hermitian of d plus star d plus and d plus star, they pair up. So this will not get any contribution from the non-zero eigenvalues. This will get contribution only from the zero eigenvalues. So this will be simply evaluate for every t non-zero. For every t non-zero, this will evaluate to the dimension of the null space of d plus star, and from the dimension of the null space of d plus star d plus. So it is the dimension of the null space of d plus star minus the dimension of the null space of d plus star d plus, but null space of d plus star is same as null space of d plus star. Similarly, null space of d plus star d plus is same as null space of d plus. So e power minus t d square, its super trace will be simply equal to dimension of the null space of d plus minus the dimension of the null space of d plus star, which is the index of d plus, So you see that the index of d plus simply becomes the super trace of this operator e power minus t d square, and this can be evaluated very simply by using the fact that d square is of the form, as we just saw, d square is of the form g mu nu x del nu plus rx scalar curvature plus fx, where this is the curvature of the Yang-Mills field, this is the curvature of the gravitational field, and this is the Laplacian with respect to the connection of both the gravitational field as well as the Yang-Mills field. So this is by using what the Getzler devised a method of calculating this super trace, and you can let t go to 0 to get the final answer. So the super trace involves calculating, first it is enough to calculate, Getzler showed that it is enough to calculate this Laplacian at a fixed x equal to 0, so that these g mu nu x become constants, and this will become locally like a Hamiltonian of a harmonic oscillator, because it is quadratic in space time derivatives and it has got such terms which are constant. And then the Getzler scaling idea, is the following: you look at a vector. How do you define Dirac gamma matrices? You take a vector space, V, and you take its anti-skew symmetric tensor product of order k. So if you take the direct sum over all k, that gives you lambda v, that is the sort of a Clifford algebra, or it is a okay. Now on this space I introduce a creation operator. I take a vector v in V and define EV. I define EV acting on say V1 wedge, V2 wedge, etc. to be equal to V wedge V1 wedge V2, etc. It is a creation operator in the Fermion-Fock space. Likewise, the adjoint of V will be what? The adjoint of V acting on V1 wedge, V2 wedge, etc. will be a contraction of V with each of these Vi. So it will be minus 1 power I V comma Vi into V1 wedge, etc. Vi you omit, so you put a cap over this, etc. Vn. This will be the adjoint. So EV star annihilates a vector V, whereas annihilates by a vector V in the Fermion-Fock space, whereas EV creates. Then the Dirac operator can be written in this space as EV plus EV star. You can check that easily, that it will anti-commute with itself. That means if you look at, if I call this as gamma V, then you can check very easily that gamma V comma gamma W, the anti-commutator plus, is simply equal to V comma W times the identity. That comes from the fact that if you take two of them, EV, EW star plus EW star EV. If you look at this, then this is nothing but V comma W into I. Like it satisfies a Clifford algebra relation. The gamma satisfies the Clifford algebra relation, and they can be derived from the fermionic creation and annihilation operators. So what Getzler did was something remarkable. He took a small parameter epsilon greater than 0 and he defined a scaling operation. So S epsilon acts on a form, let us say omega belongs to a form, say lambda k V or lambda of V. So you define this to be equal to epsilon power minus the degree of the form multiplied by omega. For example, if omega is a 1 form, then dou omega is 1. If omega is a 2 form, then dou omega is 2. So if omega is a creation operator of order k, then this will become dou omega will be k. If it is an annihilation operator, right? For example, if omega is equal to EV, then it is a creation operator. So in that case, dou omega will be plus 1. On the other hand, if omega is EV star, then dou omega will be minus 1. So what he did was, he defined S epsilon acting on epsilon, actually you should put an epsilon inverse, okay. So you are defining it as an operator on the space. So S epsilon omega S epsilon inverse is nothing but epsilon power minus dou omega omega for any form or any operator acting on the Fermion-Fock space. So if you look at S epsilon acting on EV, S epsilon inverse, what is this equal to? This is equal to epsilon power minus 1 EV, because EV has degree 1. Likewise, epsilon acting on EV star S epsilon inverse, this will be epsilon times EV star. So if you look at S epsilon acting on the Dirac operator, epsilon inverse, this will become S epsilon times EV plus EV star into S epsilon inverse, which is equal to epsilon power minus 1 EV plus epsilon power plus 1 times EV star. So if I multiply this by epsilon here, epsilon, this will become simply equal to epsilon times this, which is EV plus epsilon square times EV star, which in the limit as epsilon goes to 0, this converges to EV. That means the Getzler scaling operator acting on the Dirac gamma matrices after an appropriate scaling tends to a creation operator EV. That means this is called the classical limit. You can regard epsilon as Planck's constant. In the quantum situation, you have a gamma operator which is used in quantum mechanics. After Getzler scaling, in the limit as epsilon goes to 0, this becomes simply a creation operator. That means that the Dirac operator gets replaced by 1 forms. So likewise, if you try to compute, so using this idea, and you can also apply the scaling to bosons, that is to functions. S epsilon fx, S epsilon inverse is nothing but f of epsilon x. So you can, when you want to compute the index of an operator, of the Dirac operator, e power minus td square, you write it as, in kernel form you write it as ktxy. So that super trace of e power minus td square is nothing but the super trace of ktxx, and then you take d4x or dnx. So you can compute it in this way, and it is enough to take epsilon t going to 0. So I can replace t by epsilon t and take the limit epsilon square t and take the limit as epsilon goes to 0 of this. Now this is computed very easily by using the Getzler scaling. After applying the Getzler scaling, this will become k epsilon square t of epsilon x d4x, where k is the kernel of the Dirac operator, and in the limit as epsilon goes to 0, this Dirac operator square becomes a simple harmonic oscillator, and due to the Getzler scaling, all these functions which appear in the Lichnowsky formula for the square of the Dirac operator, namely a Laplacian plus a curvature term plus these terms, these become forms. These are actually expressed in terms of products of Dirac matrices, but in the classical limit as epsilon goes to 0, after applying the Getzler scaling, it will become a form. So you will get finally, in taking this limit, what you will get is that the index of the Dirac operator, namely super trace of e power minus td square, as this can be expressed as the index of d plus, as we saw, index of d plus, and that is nothing but simply it will be given by it will give, after you apply the Getzler scale, it will be given by a form. So it will be of the form, say, r divided by sin h r wedge product f, wedge product e power f. So it will be expressed in terms of Chern classes, and this will be an integral over the manifold, right? And when there is no curvature, then you have only e power f, and since the space time dimension is 4, this e power f, the only non-zero contribution from this will come from e power f square by 2 factorial, or equivalently f wedge f, which is precisely the index theorem which we just proved, which we just derived this form for the which we just derived through anomaly analysis. So this idea of using scaling to reduce the computation of the super trace to an integration with respect to exterior forms, an integration with respect to exterior form, it will become an exterior form integration. Wherever you have a super trace, that if you have a product of 4 gamma matrices, for example, gamma A, gamma B, gamma C, gamma D in the curvature, then after Getzler scaling, this will become simply E of VA, wedge E of VB, etc., which will reduce to a differential form. So it can be interpreted as dxa wedge dxb wedge dxc wedge dxd, or equivalently dx1 wedge dx2 dx3 dx4, which means a 4-dimensional integral. So super traces are reduced by Getzler scaling in the classical limit to an integration. In that way you are able to connect the algebraic properties of operators with integrals over topological classes, integrals of topological classes. This was the major idea in the proof of the Atiyah-Singer index theorem. Let us see from a physical viewpoint how these things are explained more easily. So what you do is you compute, you look at a Dirac operator of the form gamma mu d mu. You look at this, look at a non-zero mode. You have seen already that the identity that it will have a certain modes will be non-zero which will be paired up. So let phi k correspond to a mode of this with eigenvalue lambda k, phi kx. Then we already saw that gamma phi kx, this will have an eigenvalue of minus lambda k. So that will be paired up. So I will call this as phi minus kx. Likewise, if you look at the zero modes, let us say they are phi px and they may not be paired up. So you may have, so these are the zero modes of the Dirac operator. D phi px is equal to 0 and they need not be paired up. So you will have in general D acting on phi minus px 0 for the, so where phi p corresponds to, where phi p has an eigenvalue plus 1 for gamma phi. So this acting on phi p is equal to plus phi p, and gamma phi acting on phi minus p is minus phi minus p. That is because if phi is any 0 mode, I can replace phi by 1 plus gamma phi by 2 and 1 minus gamma phi by 2 phi. Of course one of them may be 0, in which case the 0 modes do not get paired up, but if they get paired up they will appear as phi p phi minus p. So I can write the resolution of the identity as summation phi k, where these are the non-zero modes plus the 0 modes are phi p. These are the 0 modes corresponding to eigenvalue plus 1 for gamma phi, and these are the modes corresponding, these are the 0 modes corresponding to eigenvalue minus 1 for gamma phi. So I can write the I in this way. Now if I assume, now I want to compute trace of gamma phi into t, let us say t is, I take t as the identity. I want to compute this trace of gamma phi times the identity after taking into account this gauge anomaly. So how will I go about doing it? Tell me. If I want to compute this anomaly in this way, then of course it is not just this that you want to compute, you want to compute trace of gamma phi times the square, the fourth power of the Dirac operator, right, you had. So you had to compute f of d square by m square, or you have to compute this acting on the identity. Okay, you have to compute this quantity acting on the identity, and how will I go about doing it? So you have seen that only the fourth order terms will come into the picture here. So gamma phi, if you look at gamma phi acting on, if you look at trace of gamma phi, okay, you are computing, you showed that this computation gives you an anomaly. This gives you an anomaly which is of the form, which is the integral of epsilon mu nu rho sigma f mu nu f rho sigma. Now we compute the same thing as m goes to infinity in a different way using this. So trace of gamma phi acting on phi k. First you will compute the trace of this quantity. First you will compute the trace of this quantity corresponding to the non-zero modes of the Dirac operator. That will give you summation phi k gamma phi psi phi k. But this will be 0. The non-zero modes will give you 0, because if phi k is an eigenvalue, phi k is an eigenvector of the Dirac operator corresponding to non-zero eigenvalue lambda k, and gamma phi k is another eigenvector of the Dirac operator corresponding to an eigenvalue minus lambda k, which is different from lambda k because it is a non-zero eigenvalue, and the two eigenvectors corresponding to different eigenvalues are orthogonal. So this term will drop out, you will not get any term from the non-zero modes. What about from the 0 modes? If you get, if you will compute trace of gamma phi into the identity corresponding to the 0 modes, you will get summation over p, you will get phi p gamma phi p, this plus summation over p phi minus p gamma phi minus p. Now we have already seen that phi p is an eigenvalue, is an eigenvector of gamma phi with plus 1 eigenvalue. So this is simply phi p with phi p, whereas phi minus p is an eigenvector of gamma phi with minus 1 eigenvalue. So this is phi minus p with phi minus p with a negative sign. So, this is nothing but the total dimension of the null space of the Dirac operator corresponding to eigenvalue plus 1 for gamma phi, namely it is the dimension of the left-handed it is the dimension of the left-hander chiral fermions for the 0 modes. So, I can write phi p comma phi p over p as n plus. N plus is the dimension of the 0 modes of the Dirac operator, is the number of 0 modes of the Dirac operator which are left chiral fermions, whereas summation over p phi minus p this is equal to n minus, this is the dimension of the subspace of the zeros of the Dirac operator corresponding to right-handed fermions, namely opposite chirality of phi plus. So, in other words, what I have shown is that the anomaly can also be written as n plus minus n minus, and this is precisely equal to, when alpha x was 1, we showed that this is some constant times f wedge f, trace of f wedge f, right. So, this is another way of interpreting the anomaly. Another way of interpreting the anomaly, whenever there is a gauge anomaly, then there is a disbalance between the left-handed fermions and the right-handed fermions, giving rise to a non-zero value of n plus minus n minus, and that is precisely given by this topological integral which came through an anomaly analysis. And surprisingly, this is also the index of the Dirac operator this is also the index of the Dirac operator as we just saw. So, all these things, anomalies, non-conservation of gauge currents, anomalies, asymmetry in the number of left-handed and right-handed fermions, and the Atiyah-Singer index theorem, all these things are beautifully connected in this whole analysis. Okay. And you can also talk about gravitational anomalies in which apart from trace f wedge f, there are contributions coming from the r by sin h r term due to the space-time curvature. That is, you have a manifold which has a space-time manifold which has a curvature, that will give you one contribution to the Atiyah-Singer index, and the other contribution will come from the Yang-Mills fields, namely the Chern-Simon classes of the Yang-Mills field. And in the case of gravitation, you will also get a term involving the curvature, namely r. Okay, and I think I will stop at this point. Okay, thank you.